Alright guys, so this question says to calculate the responsiveness for a critically damped system as critically damped damping ratio is equal to 1 when a unit step function is suddenly applied. So the unit step input will be RS. So this is the form for a second order system. This is the standard form. If zeta is equal to 2 is equal to 1, sorry, you're going to have this answer right. And if you factor this because this is a quadratic equation, you're gonna get this. You can try expanding this, you get back to this again. So now let's apply our unit step function. So C of S, we're going to take RS to be here, so to be times R of S, right? So now C of S is going to be equals to W square N over S plus WN square times 1 over S, because that's the unit step function in the Laplace domain. So now from here we're going to do partial fraction decomposition. So it's going to be equals to A over S. Well, because of the nature of this, we're going to have B, we call it repeating roots, S plus WN, then plus C over S plus WN square. So when you have repeating roots, this is how the partial fraction decomposition will be. We're going to take our LCM. So this will be the denominator. Usually I used to make the mistake of multiplying all of them together, but this and this are basically the same thing. So now this into the denominator of A to be AS plus WN square into this is to be BS S plus WN plus this into this will be CS. Now this denominator will cancel out this denominator. You can do cross multiplication, and then we'll expand the numerator and do something we call comparison of coefficients. So it's going to be this is going to be the expansion and the factorization, and we're going to compare coefficients. This is S squared. We look on the other side to see which other value here has a value of S squared. None of them have, so it's going to be A plus B is equals to 0. For this next one, it's going to be equals to 0 as well again. And for this last one, it's going to be equals to this because these are both constants. So to get A, you just divide both sides by WN square, which means that A is going to be equals to 1. And then from A being equals to 1, you can tell that B will be equals to negative 1. We substitute in our values here is going to be 2 times 1, so that'll be 2 WN plus minus 1 WN. So we can just erase this, so to be minus WN plus C equals 0. This is going to be equals to WN plus C, which means equals 0, which means C will be equals to negative WN. So now we just put back our values of A, B, and C to the partial fraction decomposition. We're going to be C of S equals to 1 over S plus A plus minus for B to be 1 over S plus WN. Remember it is minus 1, that's why I just change it. Minus WN over S plus WN square. Now I simply can take the inverse Laplace, which we can use this table. So 1 over S in C of T is going to be 1, which is unit step, which is 1, minus 1 over S plus WN. So for the inverse Laplace of this is going to be minus. So then you can see at this position, we can find this here. So this will be equals to E raised by minus WNT because they used A instead of WN. Minus for this last one, this has a constant. So we bring out the constant, it will leave us with 1 over S plus WN square. Now, if you look through, you're going to find that this second one, which is called the shifting theorem, is there. So it's going to be T e raised power negative W N T. You always have to look at this sign. This sign predicts what is going to be at this e raised power. Now, because of the constant, we're going to write W N at this point. So now, this is your final answer. This basically means that there'll be no oscillations because of the absence of cos and sine, and there'll be no overshoots.